folks, and welcome back to Physics with Captain Rod here. So the purpose of me making this video is to just walk through a quick, fairly simple demonstration of how to apply energy concepts to solve a problem. So what we're going to do here is imagine this person here walks to the edge of a cliff and drops their keys. And their keys are going to accelerate down, through under the influence of gravity. So I could kind of illustrate that with a motion diagram. Remember, motion diagrams kind of like little snapshots in time showing where the object is at various locations. This last picture here, right before it hits the ground, it would be moving down at some velocity here that I don't know, and maybe we'll calculate that later on. But what we're going to try to do here is calculate how long, what the delta t would be. How long do we expect it to take for those keys to hit the ground? And so we're going to start this by using principles of work and energy. So the way we apply the work energy theorem is this. We pick a location or a set of conditions here. I'm going to call this position 1 right here, where the rock is basically, or the keys are still in the person's hand. I'm going to call that t equals 0. The velocity would be 0 at that point. And my position 2 is going to be here, where the keys are just above the ground. They're just about to impact. They're moving down with a speed that I would call, well, since it's at position 2, I would call that velocity 2. And we're going to go ahead and try to use the work energy theorem to calculate that velocity. So I've labeled my position here, both positions, position 1, position 2. I'm going to go ahead and write out the work energy theorem. PE1 plus KE1 plus work from 1 to 2 equals PE2 plus KE2. Now, since we're dealing with potential energies, we need to define a datum. The lowest point in the diagram is usually a good place to do that, so I'm going to go ahead and put a horizontal line here and label that. There's my datum. And again, this is where we're going to measure potential energy from. So with the datum at this position, PE1 is now going to equal mgh, where the h is this 50 meters here. Right? Now I'm going to move on to KE1. So here's the keys at position 1. They're not moving yet, so they have a velocity of 0. And since kinetic energy is 1/2 mv squared, 1/2 mv squared, and the velocity is 0 at that point, KE1 would be 0. All right, work 1 to 2. That's going to be 0. I'm going to come back to that and talk a little bit about why after I finish the other two terms. All right, moving over to the right, equals. All right, PE2, here's the rock at position 2. It has really no height above the datum, so now its potential energy is 0. And then its kinetic energy is 1/2 mv squared. Now that v is the velocity at position 2, so I'm going to go ahead and put a subscript on there. So I'll go back to this work term. If we consider a free body of the rock, and if I picture like a free body right here, here's the rock, or I'm sorry, keys in this example. As it falls, the gravitational force is down, magnitude mg. If we included air drag, that would be up. Air drag always opposes motion, but I'm going to assume air drag away for this example. It's not a very significant force over this small distance. Now, that's it. That's the complete free body. And you'll notice there's only one force here, mg. If I did calculate the work done by gravity from position 1 to position 2, it would equal force, which is mg, times the distance I have labeled h, and that work term would be positive because the force vector is parallel to the motion, or in the same direction as the velocity. So you'll notice that mgh, we have that sitting right here. That's really what the potential energy is. The potential energy is the work that gravity does on this object, moving it from position 1 to position 2. So we've already taken gravity into account. If we try to put mgh in for gravity again, we'll effectively be double dipping on it. So we don't want to do that. So all forces have been taken into account. That's why the work term is 0. And here's our work energy theorem. Now, we don't need the zeros, and the mass is the same on both sides, so we can basically write this gh equals v squared over 2. I'm going to go ahead and drop the 2 because there's only one velocity in this problem. And if I put in our numbers here and solve this for v, I get that v is approximately, when it hits the ground, 32 meter per second. Right? I'm getting that by putting 9.8 meter per second squared here, 50 meters here, multiply by 2, and then square root both sides. And out will come about 32 meter per second. So now what I know is I know V final. It's important to note that when you use the work energy theorem and you find a velocity, that velocity is an instantaneous velocity. It's the velocity at position 2. It's not an average over the time interval or anything like that. So now what I'm going to do is I'm going to start graphically studying the motion of the keys. If I put a coordinate system here pointed down, something like this, plus x, and I were to graph then velocity against time in this set of coordinates with down positive, at t equals 0, the velocity was 0, so the first point on the graph would look like this, 0, 0. And then we know that velocity is going to increase linearly here because the acceleration is constant, right, up to some time t that we don't know yet. But we do know that the final velocity is 32 meter per second. So on the graph, that distance right there is 32 meter per second. And we can find time a couple of different ways, either by slope or by area. I'm going to go ahead and do this. We know that the change in position is 50 meters. So the change in position, 50 meters, is going to equal the area bound inside this curve here. And because this is a triangular area, we can write that as 1/2 t times 32 meter per second. And then we can solve this for t now. If we go ahead and do that, I get about 3.13 seconds. So here's an example of how we would apply the work energy theorem in a relatively simple problem, and how we would kind of couple that with a graphical study of motion here. And I hope this video helped demonstrate how we might do these things. Hope you have a great day, and I'm going to go ahead and work on another one.